Hello friends, welcome to my channel. Today I want to talk about LoRa adaptation, especially in large language models. Uh, okay, as I told you before, these slides are for Professor Vardan Papyan. He is a professor at the Department of Mathematics at the University of Toronto. Okay, let's go with the fourth session. As you have seen, large language models are state of the art in natural language processing, and it's very important to adapt these LLMs to the specific tasks that we want. In some words, we want to fine tune them, but we want it to be parameter efficient. In let me see if we have it here. Yes, we have it here. Okay, in traditional fine tuning, we have a pre-trained large language model. We want to uh, we want to specify the model for a specific task. For example, classification between good or bad comments. In a traditional way, we do the fine tuning of all the parameters of the whole model. It's very expensive. By expensive, I mean it's very time consuming. It requires high memory usage, high RAM usage, uh, and yes. But there are some ways that we call them PEFT, parameter efficient fine tuning. That one of these PEFT methods is LoRA. It wants to reduce these parameters so that when we want to fine tune a large language model, we don't use all of the parameters, but we use a portion of them, or we add some parameters and only fine tune them. Uh, okay, in LoRa, we are reducing the weight matrix. It means we are reducing the rank of the weight matrix, and so we have lower computation costs. We have lower. It would become easier and less expensive for us to fine tune this model. Okay. Uh, okay. LoRa uh, transforms the weight update matrix into two low rank matrices. What do I mean? I will discuss it later. Soon I will show you what do I mean by this. And instead of updating all of the big matrix of weights, we only update these two matrices that are multiplied by each other, and we do not change the original weights at all. Okay, so the original weights remain exactly the same, and yes. Okay, as you can see, LoRa changes the model in this way. The model has some weights W0. We do not want to change this W0. Instead, we add some new parameters, and we only change these new parameters. And these new parameters are concluded and originated from the multiplication of these two matrices A and B. And please note that they are low rank matrices, because if they are high rank, why should we fine tune them? Why don't we fine tune W0 instead? So we are adding delta W, that is low rank, instead of the high rank W0 to adapt it and fine tune it easier. Okay, so uh, as you can see here, we have a matrix A, another matrix B, and as you can see, uh, uh, its dimension is R, so it is, for example, n times R, and B is R times n. Uh, you, oh, sorry, D. It's D times R, and here is it's R times D. So the output is D times D, but it is low rank, as you can see, because D is very smaller. Sorry, R is very smaller than D. Okay, and oh, oops, let me go to the previous. Okay, this one. Okay, as you can see, for example, in full fine tuning of, for example, Rob, I think it's Roberta. Yes, it's Roberta. Uh, we have uh, 125 millions of parameters, but in LoRA we have only 0.3 million. It is 300,000 only. And again here, and again here, and the interesting point is that as you can see, we are reducing the number of parameters very much, but the accuracy does not change a lot, and sometimes it's even getting better. For example, as you can see, 19.2 turns to a little lower here, but on another task and data set, you can see that, for example, here it's getting somehow better, 92.8 to 93.3. Okay, so these are some other outputs here, and these are some other outputs that you can see. LoRa is sometimes even better than full fine tuning. Here you can see an GPT-3, and you can compare these two lines that are highlighted here. That's very different. It's it's very good. Okay. Uh, as you saw, it has a lot fewer parameters for update, but it's comparable to full fine tuning. Sometimes better, sometimes worse, and it reduces the training time and computational cost because of the previous reason, because it has fewer parameters. Uh, and it has been tested across various NLP benchmarks, as you saw, MNLI, QNLP, and etc. Uh, oh, here they are varying the R that we saw before, and as you can see, uh, even with R equals to 1, it achieves very good results. You can see here, and it's very interesting. It means that there is no need to put R something very high, and we can do it in R equal to 1. It's the lowest possible number that we can put. It's very interesting. And 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 as you saw here, we have uh, queries and values and keys, and we can we can fine tune each of these, or ignore one of them. And here we can see the effect of, for example, this time the queries, this time is about keys, this time each time for example, its values, each time we can do for different set of parameters in the transformer and a large language model. Okay, and finally, these are something that I repeated, I told you before, and it's suitable for real world applications. Lots of people are using. Thank you very much.